this video, we're going to be going over vectors. Let's jump right in. First thing that I think is important to go over is the distinction between scalar quantities and vector quantities. Scalar quantities are only going to have a magnitude, whereas vector quantities have both a magnitude and a direction. So some examples of scalar quantities might be mass and speed, since these two sort of quantities only have a magnitude. Because when you're thinking of a mass, it might be 10 kilograms, and of a speed, it might be 5 meters per second. There's no implied direction that comes with them, it's just the magnitude. But on the other hand, examples of vector quantities are velocity and displacement. For velocity, the magnitude of velocity is speed, but in addition to that, a velocity has an implied direction. For example, if your velocity is 10 meters per second, you might be heading forward at that speed, but if your velocity is negative 10 meters per second, you're heading backwards at that speed. Similarly for displacement, if your displacement is 5 meters, then you're 5 meters ahead of your starting spot. But if your displacement is negative 5 meters, then you're 5 meters behind it. And so you can see with vector quantities, we not only have the magnitude, but also the direction. Now when we're thinking of a vector on a plane, what that's going to be is a line segment with a given direction. So let's say we have this coordinate plane, and on that plane we have the point A and the point B. Then the vector AB is going to be the line segment that points in the direction of B, starting from A. For this vector AB, which we write with the arrow over it, that's just notation, the direction is from A to B, and the magnitude of the vector is just the length of the line segment. And the notation we use to show the magnitude is the following. So it's similar to the notation we use for absolute value, but they're not the same thing. Now, if we were to express the vector AB in vector form, would be the following, where A is the horizontal component and B is the vertical component of the vector. So for our vector AB, the horizontal component would be this, and the vertical component would be this. Another point of terminology that I forgot to include on the first slide was that A, the starting point of the vector, we call the initial point, and B, which is the sort of ending point, we call the terminal point. And just to continue with our vector AB, if the initial point A has the coordinates x1, y1, and the terminal point B has the coordinates x2, y2, then the vector AB will have a horizontal component, which once again is this sort of component of the vector, will be x2 minus x1, and the vertical component of the vector, which is this, would be y2 minus y1. Based on that information, let's do the following problem. Find the component form of vector u with initial point -1, 3 and terminal point 2, 6. So I'm just abbreviating initial point and terminal point as IP and TP. So this vector u is going to have two components, right? The horizontal component of vector u. The horizontal component of the vector u is going to be the x-coordinate of the terminal point, x2, minus the x-coordinate of the initial point, -1. So that's 2 minus -1. And the vertical component is going to be the y-coordinate of the terminal point, y2, minus the y-coordinate of the initial point, which is 3. So 6 minus 3. And if we simplify this, we get 2 minus -1 is 3. And 6 minus 3 is 3 as well. And just to verify that we have the right answer, let's think of it this way. So we start at the point -1, 3, and we want to end up at the point 2, 6. If we think about just the x-coordinates, we want to get from -1 to 2, so our horizontal component has to be 3, and in terms of the y-coordinates, we have to go from 3 to 6, so our y-coordinate has to be 3 as well, and so the vector u is 3, 3. Now let's consider this variation. If vector v, which has the component form 2, 4, has the initial point 1, -3, what is the terminal point? I think the best way to think of this problem is just visually. Let's say the initial point is right here. Let's say this is 1 comma negative 3, and the vector v has the component form 2 comma 4, then that means the horizontal component of the vector is 2, so we're going to move 2 units to the right in the x direction, and the vertical component is 4, so we're going to move 4 units up in the vertical direction. And so if we draw this vector, it's going to look something like this, but then it becomes clear that the x-coordinate of the terminal point is 1 plus 2, which is 3, and that the y-coordinate of the terminal point is negative 3 plus 4, which is 1. And so 3 comma 1 is the coordinates of the terminal point. Now, once again, let's come back to our vector AB, and now let's talk about how we can calculate its magnitude. We're dealing with the vector AB, which has horizontal component A and vertical component B. So let's draw those components in again. The magnitude of this vector, which, as I mentioned earlier, we can write with the following form, is going to be the square root of A squared plus B squared. So to find the magnitude of a vector, you take the square root of its horizontal component squared plus its vertical component squared. And as you may suspect, this comes from the Pythagorean theorem. This triangle that we formed with the vector and its components, the length of this leg of the right triangle is A, the length of this leg is B, and the length of the hypotenuse is the magnitude of the vector AB. And so the Pythagorean theorem tells us that A squared plus B squared equals the magnitude of AB. And from here, if we take the square root of both sides, we get this formula. Alright, now let's do this problem. So we have to find the magnitude of this vector and the magnitude of this vector. So let's start by finding the magnitude of vector v. The magnitude is going to be equal to the square root of its horizontal component squared, which is negative 1 squared, plus its vertical component squared, so 3 squared. This is equal to the square root of 1 plus 9, which is 10. And so the magnitude of vector v is root 10. And what this means is, if you draw the vector v, which is negative 1, 3, the length of that vector is root 10. Alright, now let's do the same for the vector u. The magnitude of u is going to be equal to the square root of its horizontal component 3/5 squared plus its vertical component squared. This is equal to the square root of 3/5 squared is 9 over 25, and 4/5 squared is 16 over 25. And so what we have here is the square root of 25 over 25, which is the square root of 1, which is 1. And so the magnitude of vector u is 1. We give a special name to vectors which have a magnitude of 1. Vectors of magnitude 1 are called unit vectors. And this is something that we'll come back to a little bit later. One notational thing that I wanted to touch on before we move on is that you'll often see vectors written in component form, a comma b, like we've gone over so far in this video, but at the same time, you might see that vector written as ai plus bj. And so these are exactly the same thing. So for example, if you have the vector negative 1 comma 3, you can rewrite that as negative 1i plus 3j, and the vector 3/5 comma 4/5, you can rewrite it as 3/5 I plus 4/5 j. And similarly, if you had the vector u is equal to 6i plus 2j, that vector in component form would be 6 comma 2. Now let's talk about the algebra you can do with vectors. Let's say you have the vector u is equal to a1, b1, and the vector v, which is equal to a2, b2. If you were to sum up the two vectors, that is to u plus v, the result would be another vector with horizontal component a1 plus a2 and vertical component b1 plus b2. If we want to think about this visually, let's say this is our vector u, and this is our vector v. If we wanted to add the vectors, that is and we did u plus v, visually it would look something like this. And we would use the terminal point of vector u as the initial point for vector v. And the vector u plus v will go from the initial point of u to the terminal point of v when we place them in this orientation. So this pinkish color vector will be u plus v. And when we look at it this way, this formula makes more sense because the horizontal component of u plus v is the horizontal component of u plus the horizontal component of v, that is a1 plus a2, and the vertical component of u plus v is the vertical component of u plus the vertical component of v, so b1 plus b2. And so hopefully that made sense. Now before we go over what happens when you subtract one vector from another, let's go over what happens when you multiply a vector by a scalar. So let's say c is our scalar, it's some constant, and we multiply that by our vector u. The resulting vector would be c times u1 times a1, comma, c times b1. And so when we multiply a vector by a scalar, we multiply each of the components of that vector by that scalar, and by doing this, we can change the magnitude of the vector, and in some cases, even the direction. For example, if we take this vector and say that's u, then the vector 2u would point in the same direction, but be twice as long. So this would be 2u. The vector negative u, which we would get by multiplying our vector u by the scalar negative 1, would have the same magnitude as u, but the opposite direction. And so basically the point here is that we can manipulate the magnitude and direction of our vector by multiplying it by a constant or a scalar. And so for example, let's say u is equal to 2, negative 3, and we wanted to find what negative u over 2 is. We're multiplying the vector u by the scalar negative 1/2. So we're going to multiply each of its components by negative 1/2. So 2 times negative 1/2 is negative 1, and negative 3 times negative 1/2 is 3 over 2. And so in relation to the vector u, the vector negative u over 2 would have half the magnitude and point in the opposite direction. Now let's come back to what happens when we subtract one vector from another. So we have u minus v. Keep in mind that we can rewrite this as u plus negative v. Negative v, we're just multiplying the components of v by negative 1, and so negative v is just negative a2, comma negative b2. And so if we sum up u and negative v, we're going to get a1 plus minus a2, so a1 minus a2, and b1 plus minus b2, so b1 minus b2. Now let's put this to work. Let's say we have the vector u equals 2, 5, and the vector v equals negative 1, 1. Let's find the following. Let's find u plus v, u minus v, and 2u plus 3v. For u plus v, we're just going to sum up the components. So that's 2 plus negative 1, which is 1, plus 5 plus 1, which is 6. For u minus v, we're going to subtract the components of v from the components of u. So that is 2 minus 1, comma 5 minus 1, which is 4. And so u minus v is 2 minus 1, which is 3, comma 4. Now let's do 2u plus 3v. 2u is 2 times 2, comma 5, and to that we're going to add 3v, which is 3 times negative 1, comma 1. 2 times the vector 2, 5 is the vector 4, 10, plus 3 times the vector negative 1, 1, which is negative 3, 3. And if we sum these two vectors up, we get 1, 13. And so 2u plus 3v is the vector 1, 13. Now let's come back to talking about unit vectors. As we mentioned earlier, unit vectors, let's say we call it u, will always have a magnitude that is equal to 1. And so let's say we had the vector a, b, and we wanted to convert it to its unit vector. Well, first off, let's think about what converting v to its unit vector will do. And so by converting v to a unit vector, what we're doing is maintaining the direction of v, but making its magnitude 1. And so to convert a vector v to a unit vector, and so the unit vector, which I'm going to represent with the letter u, v divided by the magnitude of v. That is, we're multiplying the vector v by the scalar 1 over the magnitude of v. If we do this, we're going to get the horizontal component of v, which is a, over the magnitude of v, comma, the vertical component of v, which is b, over the magnitude of v as well. Since the magnitude of v is going to be a positive quantity, since length is always positive, we're not going to be altering the direction of v. And so now we just need to verify that by doing this calculation, we're going to get a vector of length 1. That is, we need to verify that the magnitude of u is 1. And to do this, let's use the formula we went over earlier. The magnitude of u is going to be equal to the square root of the sum of its components squared. So in this case, that's a squared over the magnitude of v squared plus b squared over the magnitude of v squared. And this is equal to the square root of a squared plus b squared over the magnitude of v squared. And let's remember, v is the vector a comma b, so the magnitude of v is the square root of a squared plus b squared. We went over this earlier, right? And so if we square both sides, we get the magnitude of v squared equals a squared plus b squared. And if the magnitude of v squared is equal to a squared plus b squared, when we divide those two things, we're going to get 1. So the magnitude of u is going to be the square root of 1, which is 1. And so we've also shown that we've converted v into a unit vector that has the same direction and a magnitude of 1. Now let's do a practice problem. Let's say v is equal to -1, 3. Let's convert that to a unit vector. We're going to do this by doing v over the magnitude of v. The magnitude of v is the square root of -1 squared plus 3 squared, which is the square root of 1 plus 9, so the square root of 10. And so the unit vector u for the vector v is the horizontal component of v, which is -1, over the magnitude of v, which is root 10, comma, the vertical component of v, which is 3, over the magnitude of v as well. This unit vector u will have the same direction as v, since we multiplied by a positive coefficient, and its magnitude will be equal to 1, as we showed in this proof. Alright, the last thing I want to go over is the direction of a vector. Let's say vector v has direction theta. What does this theta mean? Well, theta, in this case, theta is going to be the smallest positive angle between the vector and the positive x-axis. For example, if this was our vector v, the direction would be this angle. Let's say we're given the magnitude of a vector and its direction. We should be able to express that vector in component form. If we split up the vector into its vertical and horizontal components, then we can use trigonometry, the magnitude of the vector, and the direction angle to find the length of those components. The vertical component will be the magnitude of v sine theta, and the horizontal component will be the magnitude of v cosine theta. So, for example, if vector v has magnitude 2 and the direction 30 degrees, let's find the component form of v. Well, based on this diagram, the component form of v is going to be equal to the magnitude of v cosine theta, which is the horizontal component, comma, the magnitude of v sine theta, which is the vertical component. we're given the magnitude of v, it's 2, and theta is 30 degrees, so this is going to be cosine of 30, comma, the magnitude of v, which is 2, times sine 30. Cosine 30 is root 3 over 2, so we have 2 times root 3 over 2, so just root 3. Sine 30 is 1/2, so we have 2 times 1/2, or 1. And so the vector that points in the direction 30 degrees with a magnitude of 2 is root 3, comma 1. Now, one last thing I want to add before we end off the video is how to find the direction theta if you're given the vector. Tangent of theta is opposite over adjacent, and so it should be equal to the vertical component over the horizontal component, so b over a. So theta is going to be the arctangent of b over a. And so if we're given the vector negative root 3, comma 1, then you know that theta is going to be equal to the arctangent or inverse tangent of b, which is 1, over a, which is negative root 3, and the arctangent of negative 1 over root 3 is 150 degrees, or 330 degrees. That is if we ignore the domain of arctangent for the moment. And how are we going to pick whether it's 150 or 330? Well, let's really quickly just draw a figure. So if this is our coordinate plane, the vector negative root 3, comma 1 is going to put us somewhere in the second quadrant, since the horizontal component is negative and the vertical component is positive. And when we look at this figure, the direction theta is this angle, and this angle is clearly less than 180 degrees, which means that theta for this particular vector must be 150 degrees. Alright, so that wraps it up for this video on vectors. I hope you found it helpful, and if you have any questions, leave them in the comment section below. Now, if this video did help you out, please do consider leaving a like, and make sure to subscribe if you want to be notified when I post more content like this. Thanks for watching.